Imagine an application that needs another application. Not tomorrow, right now. It has an address written down, a number, an IP address, the kind of thing that feels solid because it looks like coordinates. Then the destination vanishes. In Kubernetes, that is not a rare disaster. It is Tuesday. A pod is a temporary home for a running process. When it dies, or when the cluster reschedules it, or when a deployment rolls forward one replica at a time, the old home is gone, a new one appears, and the new one does not inherit the old number. The application that memorized the address is now shouting into an empty room. This is the problem service DNS exists to solve. Not elegance, not fashion, survival. If the thing you need keeps moving, what are you allowed to remember? A number that expires or a name that is supposed to stay true? The rest of this story is about that bargain, and about the quiet machinery that has to keep the name honest while the cluster underneath never sits still. Before Kubernetes ever entered the picture, the internet already had an answer to moving destinations. It was not a map of streets, it was a directory. DNS records are an address book. A name people can remember is translated into a number machines can route. An A record points a name at an IP address. An MX record points mail at a mail server. A C name is an alias, one name standing in for another. None of that is Kubernetes specific. It is the same idea that lets you type a website instead of a string of digits. Proper management of those records is what keeps connectivity from becoming a scavenger hunt. The cluster will steal that idea and put it inside a private world. But first, feel the original bargain. Humans and programs prefer names. Networks prefer numbers. Something has to sit between them and keep rewriting the page whenever the number changes. If that rewrite is late or wrong or missing, the name becomes a lie. That is the tension we will carry all the way to the last scene. Kubernetes takes that address book idea and installs it as an internal service. Pods and services can talk using names instead of IP addresses. Whenever a service is created, the cluster automatically assigns it a unique DNS name. Applications can keep calling that name even when the pods behind it are replaced and their IP addresses change. That sentence is the whole promise. Notice what it does not promise. It does not say every pod is immortal. It does not say every address is forever. It says, you do not have to chase the moving parts yourself. Modern clusters, by default, hand this job to CoreDNS. The name is the stable handle. The resolver is the living directory. The service is the object that sits in the middle, a communication point that is supposed to remain while replicas come and go. If that directory works, a deployment can roll, a node can fail, a pod can be evicted, and the caller still has something true to say. If it fails, the cluster still looks busy. The names just stop leading anywhere. That is why this is not a footnote. It is how a dynamic system becomes usable. Look at the cluster as a building, not as a single room. Outside, one Kubernetes cluster. Inside, nodes. And inside those nodes, namespaces. Partitions that keep teams, environments, and applications from colliding. The diagram you would draw is almost stubbornly repetitive, and that is the point. Each namespace can hold the same kinds of objects: a service, a pod, a deployment. App 1 and App 2 can live side by side in more than one namespace. The icons look identical, the names can look identical, the identities are not. A namespace is a neighborhood. The same street name in two neighborhoods is not the same house. Kubernetes DNS is namespace aware. A query is not just find nginx, it is find nginx here. If you forget the neighborhood, you can get a perfectly valid answer to the wrong question. The diagram is not decoration, it is the first warning. Identity in this system is local before it is global. The cluster can contain many copies of the same idea. The directory has to know which copy you meant. A service is not a pod with a nicer name. It is a stable communication point in front of pods that are allowed to disappear. Kubernetes automatically assigns a DNS name to each service. That name is what applications are supposed to remember. The pods behind it can be recreated. They can land on a different node. They can receive a new IP address. The service is the thing that is meant to stay. Think of it as a reception desk that never changes its listed number, even when the staff in the back office rotate every hour. Callers do not need the private extension of whoever happens to be on duty. They need the desk. That is why service DNS records ordinarily resolve to the service's own address, a virtual IP that represents the desk, not the current occupant of a particular chair. The pod is the occupant, the service is the listed number. Confuse those two and you will hard code the chair. Then the next rotation will look like an outage. The cluster did what it was designed to do. Your memory did not. Here is the catch that makes the reception desk metaphor incomplete. The same service name can exist in more than one namespace. Query results depend on where you stand. A short name is resolved relative to the caller's namespace. Two teams can both create a service called NGNX. One lives in default, one lives in staging. Both names are legal, both can be healthy, they are not the same destination. This is not a bug, it is isolation doing its job. But it is also how a careful engineer ships a perfectly spelled name and still lands in the wrong neighborhood. The source is blunt about this. Namespaces affect query results. Context is not extra credit, it is part of the name. So the directory cannot be a single flat phone book for the whole cluster. It has to be a set of books, one per neighborhood, with a way to write the full address when you truly mean a particular one. That full address is coming next. Until you have it, every short name is a local word, useful, fast, and dangerous if you forget which room you are standing in. The full name is not poetry. It is an address written in layers. Take this one exactly, ngnx.default.svc.cluster.local. Read it from the left, the way a human does, then from the right, the way the directory does. ngnx is the service. Default is the namespace. SVC says this object is a service, not some other kind of name. Cluster.local is the cluster's DNS domain, the private country in which these names are legal. Together they form a fully qualified name. Inside the default namespace, an application can often just ask for ngnx and get the same answer. The short form is a courtesy of search paths. The long form is the passport. If you need to reach a service in another neighborhood, the short word is not enough. You write the whole chain. This is the moment the story stops being metaphorical. The name is structured. Each dot is a claim about identity. Drop a segment and you have not abbreviated. You have changed the question. The cluster will answer the question you actually asked. It will not correct your sense of which neighborhood you meant. So now we have two ways to speak, a local nickname and a full civic address. Applications inside the same namespace can use the service name alone. That is convenient. It also hides the machinery. The resolver is quietly completing the rest of the name using the pod search list. Typically the namespace, then SVC, then the cluster domain. When that completion is what you intended, it feels like magic. When it is not, it feels like a haunted cluster. The documentary beat here is simple. Convenience is a search path, not a second identity. There is still only one real name. The short form is a local pronunciation. Cross a namespace boundary and the pronunciation fails. Teams that copy a snippet from a tutorial often copy the nickname and paste it into a different neighborhood. The letters match, the destination does not. Naming solved the moving IP. It did not abolish place. The next question is no longer what the name looks like. It is who sits up all night rewriting the directory so that name still points at something alive. The Night Watch has a name, CoreDNS. It is a flexible, extensible DNS server written in Go, and it is the default DNS server in modern Kubernetes clusters. It resolves queries for services and pods, and this is the part that makes the earlier story possible, it automatically updates DNS records when cluster resources change. Without that automatic rewrite, the stable name would be a museum label on an empty case. A pod dies, a new pod appears, endpoints change. If the directory still recites yesterday's number, the name has become a rumor. CoreDNS is built as a chain of plugins. Administrators customize behavior through a file called the core file. That architecture is not a trivia fact. It is why the same server can be a quiet default in one cluster and a carefully tuned instrument in another. The cluster did not merely add DNS, it added a living process whose job is to notice change. The unresolved worry, already visible, is that a living process can also be misconfigured, overloaded, or simply unhealthy. A directory that writes is also a directory that can write the wrong thing. Hold the feature list the way a reporter holds a job description, not a brochure. CoreDNS is the default DNS server. It resolves names for services and pods. It updates records when the cluster changes. It supports plugins for customization. It is configured through the core file. 5 sentences, 1 occupation. Default means you may never have chosen it, and it is still in the path of every name lookup your applications make. Resolution means it is not a blog post about names. It answers questions in real time. Automatic updates mean the story of the moving pod is supposed to be invisible to the caller. Plugins mean the behavior is not a sealed box. The core file means there is a single place where that behavior is declared, and therefore a single place where a typo can go to war with the entire cluster. This is the quiet power and the quiet risk in the same object. The next chapter of the history is why this object replaced the one that came before it. Replacements always claim to be improvements. We should hear what the older system actually was before we accept the verdict. Kube-DNS was the original. It provided DNS-based service discovery for services and pods. It automatically created and managed records inside the cluster so applications could speak names instead of IP addresses. That mission is the same mission. The difference is not the dream, it is the machine. In modern Kubernetes, CoreDNS replaced Kube-DNS as the default, the source says, because of improved performance, flexibility, and extensibility. History matters here because people still meet both names in old manifests, old blog posts, and old clusters that were never rebuilt. If you treat them as synonyms, you will misread a troubleshooting guide. If you treat CoreDNS as a totally different idea, you will miss the continuity. Both are answers to the moving address problem. Kube-DNS was specialized for the cluster. CoreDNS is a general-purpose DNS server that happened to become the cluster's default. That shift, from a purpose-built appliance to a modular instrument, is the real plot of the comparison table we look at next. The question is not which logo is newer, it is which design can keep rewriting the directory as the cluster's needs get stranger. The comparison is a 3-row argument: architecture, extensibility, performance. KubeDNS is based on SkyDNS and is mainly trained, the table says, for a Kubernetes cluster. CoreDNS is a general-purpose DNS server with a modular design. On extensibility, KubeDNS has limited options. CoreDNS is highly extensible through middleware plugins. On performance, KubeDNS is described as optimized for Kubernetes workloads and efficient service discovery. CoreDNS is described as efficient with configurable caching. Read that again without picking a winner too fast. The older system is not portrayed as broken. It is portrayed as specialized and constrained. The newer system is portrayed as modular and tunable. Flexibility is the claimed advantage. Flexibility is also how you invent a unique failure. A plugin chain can do more. A plugin chain can also be assembled into something that no longer answers the simple question: what is the address of this service right now? The table is a fork in the road. One path is a smaller, cluster-shaped tool. The other is a workshop. Most modern clusters took the workshop. That choice only pays off if someone knows how the workshop is arranged. The workshop has a floor plan. It is called the core file. This is the configuration CoreDNS reads to decide which plugins run, in what order, and for which zones. It is not an application you click. It is a text declaration of how the directory thinks. In a typical cluster, you will see a zone for the cluster domain, a Kubernetes plugin that watches services and endpoints, a cache, a forwarder for names that live outside the cluster, and health or ready checks so the platform can tell whether the directory is actually alive. Change the core file and you are not decorating the server. You are changing what a name means. That is why later setup steps treat an update to CoreDNS and the core file as a deliberate act, followed by verification. A configuration file that sits this close to every lookup is a loaded object. Handled well, It lets a cluster grow extra behaviors. Stub domains, custom caches, special forwarding. Handled carelessly, it is how an entire neighborhood goes dark at once. The name still exists. The path from name to number has been rewritten under your feet. Kubernetes creates DNS records for services and for pods. Those are not the same kind of entry in the book. A service record is the listed number for a role. A pod record, when it exists for your purposes, is closer to the private extension of a particular instance. Most applications should call the service. That is the point of the reception desk. But the directory is capable of more than one kind of truth. A normal service answers with a single service IP, the virtual address that represents the role. A headless service, which we will meet properly in a moment, can answer with the addresses of the backing pods themselves. The source is careful. Headless services return pod-related results. Normal services return a single service IP. That split is not academic. It decides whether the caller is allowed to see the moving parts. Some workloads want the desk. Some workloads, clustered databases, peer-to-peer members, anything that must know its siblings, want the people in the room. DNS is how both wishes are expressed without hard-coding yesterday's chairs. The record type is the next instrument in that expression. An A record is an IPv4 address. An AAAA record is an IPv6 address. In this story, they are the simplest possible answer to the question, where is that name? For a normal service, those address records point at the service's stable virtual IP. The pattern looks like a service name, then a namespace, then SVC, then the cluster domain. You have already seen the concrete form, nginx.default.svc.cluster.local. The same pattern appears with other service names, my-service in its namespace under the same cluster domain. This is the everyday path. An application asks for a name. The directory returns one address that represents the service. Traffic then depends on the cluster's networking to reach a healthy pod behind that address. DNS did not pick the pod. DNS picked the desk. If you expected to see 3 pod IPs and you only see one service IP, you are not looking at a broken lookup. You are looking at the normal contract. The next scene is the exception that people chase when that contract is too coarse, when one address is not enough information. Sometimes the desk is the wrong abstraction. A headless service has no cluster IP of its own in the usual sense. DNS is allowed to return the IPs of the backing pods. The caller sees the room, not a single listed number. That is powerful for workloads that must address members individually, elect a leader, form a quorum, or keep session affinity to a particular peer. It is also a different kind of honesty. The answers can change more visibly. Pods appear and disappear, and the set of addresses in the response changes with them. Automatic updates matter even more here, because the name is no longer shielding you from churn. It is publishing the churn. If you treat a headless lookup like a normal service lookup, you will write a client that expects one address and receives many, or receives a set that shifts under you. Flexibility is not free. It changes the shape of the truth the directory is willing to tell. And once you start telling richer truths, you also start using richer record types. Address records say where. SRV records say how to reach a named port. SRV records answer a more specific question. Not just where is the service, but which named port on which protocol should I use. They are especially useful for headless services, where clients may need both the instance and the port identity. The naming pattern includes the service, the protocol, the namespace, and the cluster domain. It is another layered address, this time carrying service and protocol in the name itself. You can inspect these records the way an operator inspects any other DNS answer, with queries from a terminal, looking at what the cluster actually returns rather than what a diagram promised. Screenshots of those queries are not trophies, they are evidence. The directory's truth is whatever it answers at that moment. If the SRV record is missing, the named port is not discoverable that way, no matter what the service object looks like in a YAML file. If the address records and the SRV records disagree with your mental model, believe the answers and then ask why the model drifted. This is the first time the story hands you a flashlight. The next chapters are about what you do when the flashlight shows an empty room. By now, the directory has a personality. It creates records automatically, it resolves with namespace awareness, it keeps service names stable while pods move, it updates as the cluster changes, it can support headless services when one virtual IP is the wrong story. Those are not 5 separate products, they are 5 facets of one bet, that a name can outlive an address. Service discovery is the everyday use of that bet. An application does not scrape a list of IPs at startup and pray. It asks the cluster by name for the current truth. Customization is the advanced use of the same bet, changing how the directory thinks so that special domains, caches, or forwarding rules fit a particular organization. Both uses assume the directory is healthy. That is the hook hanging over the next chapter. The more useful the name becomes, the more of the cluster's life depends on a process you might never have deployed by hand. Initial setup looks boring until you remember what it is installing. The only reason ngng means anything at all. The source lays out a sequence, and the sequence is a plot. First, choose a DNS solution for the cluster. In modern defaults, that choice is often already made for you, CoreDNS, but a choice it remains, especially on older or custom platforms. Second, install the DNS add-on so the server actually runs inside the cluster. A design document is not a resolver. Third, customize if your organization needs something beyond the default, extra zones, forwarding, plugin behavior. Fourth, update CoreDNS and the core file when that customization or an upgrade requires it. Fifth, verify. Ask real names, confirm real answers. Sixth, monitor and maintain, because a directory that is correct on Monday can be stale on Thursday. Notice the order. You do not customize before you have a server. You do not congratulate yourself before you verify. You do not treat verification as a one-time ceremony. The cluster will keep changing. Maintenance is not a personality trait. It is the admission that automatic updates only work if the updater itself stays alive and correctly configured. Skip a step and the failure often shows up far from the file you edited, in an application that simply cannot find a friend. Customization is where the workshop stops being a metaphor and becomes an incident report waiting to happen. Incorrect configuration can make a name unresolvable or resolvable to the wrong place. Stale records can survive after pods have moved. Networking problems can make the DNS service itself unreachable even when the records are perfect. Unhealthy DNS components can fail quietly because the symptom is always somewhere else. A timeout, a fallback, a confused client. This is the cost of a living directory. The same automatic rewrite that saved you from hard-coded IPs can freeze if the watcher is broken. The same plugin flexibility that made CoreDNS the default can route a query into a black hole. None of that means you should never touch the core file. It means every change is a change to the cluster's sense of place. Treat it with the seriousness you would give a rewrite of every street sign in a city overnight, with no public announcement. The applications will not file a ticket that says core file. They will say they cannot connect. Your job is to hear the directory in that complaint. When the name fails, the source offers a checklist that is really a theory of blame. First, the pod network. If packets cannot move, DNS is not your first mystery. It is a casualty. Second, DNS service health. Is the resolver running? Is it ready? Can other pods reach it? Third, DNS configuration. Is the core file what you think it is? Are search paths and cluster domain what the names assume? Fourth, pod resolvability. Can this particular pod be named and reached the way you believe? The order matters. People start at the application and work downward, cursing a service name while the network under the resolver is partitioned. Or they restart CoreDNS forever while the configuration is simply wrong. Or they fix the server and never notice that one namespace's search path is completing names into a different neighborhood. Troubleshooting is not a ritual of restarts. It is asking which layer of the story broke: the road, the directory's pulse, the directory's text, or the particular house you hoped to find. Each answer sends you to a different repair. The same symptom, name not found, no such host, a hang, can come from any layer. That is why the checklist exists. We opened with an application shouting into an empty room, holding a number that had already expired. That is the stake. Service DNS is the reply. Remember a name. Let the cluster keep the number honest. Kubernetes assigns names to services. Namespaces decide which neighborhood a short word belongs to. A full name like nginx.default.svc.cluster.local is the passport when you cannot afford local slang. CoreDNS, having replaced Kube-DNS as the default, rewrites the directory as pods come and go. Normal services hand you one stable address. Headless services can hand you the pods themselves. SRV records name the ports. Setup, customization, and troubleshooting are how that reply stays true instead of becoming folklore. What the name made possible is ordinary and enormous. Applications can keep calling the same word while the infrastructure under them is replaced. Deployments can roll, nodes can fail, the reception desk stays listed. The unresolved question is the one the field is still living inside. How do you keep discovery trustworthy when the thing being discovered never stops changing, and when the directory itself is just another workload that can be misconfigured, partitioned, or quietly late? The address will move. The name has to earn its keep every minute after that.